Yeah, so today from 9 to 9:30, we have a talk by Pablo Ordejon. He did a PhD in physics in Madrid's Autonomous University. And then he worked as a postdoc and research and professor in Illinois and Oviedo. And then he moved to Barcelona. And during this time, he was one of the early developers of Siesta. And currently, he's the group leader at the Theory and Simulation Group at ICN2. So he's my group leader. And also, he acts as a director of the center. So right now, he's a very busy man. It's hard to catch him for a meeting, but when you do, he knows everything. So he will solve your entire thesis. So I hope you enjoy his lecture on electrochemistry, on the work we have been doing on electrochemistry with Transiesta. So all yours, Pablo.
Okay, thank you, Paul. So let me try to share the screen with you. Let's see if it works. Okay, so can you see the slides?
Yes.
Okay, so I'm going to give this presentation on using Transiesta to deal with electrochemical problems. And that's a very recent development, very recent work. Actually, it's not published yet. It's the very first steps in trying to use Transiesta to describe electrochemistry problems. And what we have done so far is to address the electrified water metal interfaces using Transiesta, so using the Noether-Lewis function. So as Paul was saying, I'm the group leader at the Theory and Simulation Group at ICN2 and also the director. And I have to thank Paul and Hernane very much for preparing the tutorial that you are going to be doing after the talk and for organizing all these meetings. So part of this work was financed and promoted by the MAX Center of Excellence in Supercomputing Application. That's an European network in ab initio simulations in materials in very large HPC infrastructures. I work at the ICN2, and Hernane also works at ICN2, but also at RMIT, the Royal Melbourne Institute of Technology in Australia. So the idea of this talk, or this work we are doing, is try to understand processes that happen at the interface between liquids or electrolytes and solids, and in particular metals or semiconductors. So in cases where you have some external applied voltage on your system, on your electrode or your metallic lead, that leads to some chemical reactions on the surface and charge movements, and that leads to some currents. And there's an interplay between all these three factors, the external potential, the chemical reactions, and the currents. And that's in the core of many processes that are important scientifically and technologically. So for instance, corrosion has all these three ingredients. New technologies for energy, like water splitting, or technology in batteries or fuel cells, those also always involve interfaces between liquids or electrolytes and solids, and all these three factors of potentials, chemical reactions, and currents. And some other things which are a bit farther from energy applications, maybe, for instance, devices to measure the brain activity, for instance, or the neural activity. So you build these electrodes which are based on transistors made of graphene, but those transistors are not solid-state transistors. They are particle state, but the gate is a liquid electrolyte. So you can measure the neural activity with this kind of devices. Some people in our institute are doing that. And this also involves this kind of science of processes. So we want to understand these processes at the atomic scale, both to get a deeper understanding of the science of it, but also to accelerate discovery of new materials and new devices that can take a profit of these properties, and especially in the energy applications. So to do that, you have to solve, or you have to understand what happens at the microscopic level very near the surface. And this is a typical plot of what is called the double layer. So you have a solid in which you have some potential that leads to some surface charge. And in the electrolyte or in the liquid, you may have some a liquid which is polar, so the molecules can polarize at the surface and form some screening dipoles here. But you may also have ions in solution, which are typically solvated, and these ions will also accumulate to screen out the charges in the metal, and you form this so-called double layer. But you also form this diffuse layer where the solvated ions are more dispersed, but there is a distribution of these solvated ions along as a function of the distance to the surface. And all these things happen at a microscopic level. Actually, the diffuse layer, the double layer happens in nanometer scales. The diffuse layer can happen at much longer scales, micrometer maybe, depending on the concentration of ions and so on. But what we want to do is to understand all this from the atomistic point of view, at the atomistic level. You may have, for instance, more complex processes in which the solvated ions get very near the surface and get stripped out of their solvation layer, and they get attached directly to the solid. And this is what is called specifically absorption, and we will see some examples of that in the talk. So these are the kinds of things we want to understand. What is the structure of the double layer? What chemical reactions occur in the interaction between the metal or the solid and the liquid and the electrolyte? What are the currents, both Faraday, so coming from chemical reactions, and not Faraday, so just capacity or capacitance currents? And what is the effect, of course, of the applied external potential? And what is the challenge for atomic simulations or for first principle simulations? There are two major challenges. One is it has to do just with the geometry of the system of your problem. This is a geometry which is not a crystal, is not periodic. So you have an open system in which you have an infinite system with open conditions, so electrons can flow in and out. So what you define are intensive quantities, are chemical potentials, temperatures, and so on, and not extensive quantities. And that's a problem for ab initio simulations. Then you have semi-infinite electrodes. The electrodes are metallic leads, which are essentially bulk. They are not microscopic, and they are semi-infinite. So that's a problem also for calculations. And they are non-periodic. A crystal is also infinite, but it's periodic, so you can apply Bloch theorem, and you can solve it. In this case, the system is infinite, but it's non-periodic. And then there are other problems that have to do with the fact that the system is out of equilibrium. It's not a system in thermodynamic equilibrium. You have a driving force, an external force, which is, in particular in this case, is that you have two different Fermi levels. You have two different chemical potentials. You attach a battery to your electrodes, and that creates two different chemical potentials in the two electrodes. And that's a system which is out of equilibrium. And that's typically difficult to describe with ab initio. So the chemical potential is not unique. There are reactions and there are currents flowing. So the idea is that this is the same kind of problems that you have in electronic transport in nano devices. And this is precisely what Transistor is able to solve. This is precisely the same kind of problem. And recently there have been several proposals to use the technology developed for transport in the nanoscale, for electronic transport in the nanoscale, to the problem of electrochemistry. And this is, I think, the first clear paper that proposes this approach. There is a previous paper by the people in Denmark, also in the Denmark University, that doesn't propose it so explicitly, but where I think the idea is already included there. So this is something which is not really new, the idea, but what I'm going to show is how to apply that in practice and how what kind of science and physics can you get out of it. So then the idea is to use all the technology developed in Transistor for the case of electronic transport, where you're interested actually in the electronic flow, in the flow of electrons through a molecule or through a nano device. So you also put two different chemical potentials that you achieve connecting your electrodes to an external battery. But here you're interested in the electrons flowing from one electrode to the other. In the case of electrochemistry, things are much more complicated because you have some chemical reactions on the interface between the electrolyte and the electrode that gives you some currents, but the current flowing through the electrolyte is not electronic. There are no electrons flowing from one electrode to the other, but it's just the ions. So there is ionic motion that leads to the currents, and there is electronic motion that leads to the chemical reactions at the interface. So this is a more complicated problem, but formally you can address it solving the electronic structure equations just the same way as you would use in electronic transport. It's only that here you have to take into account the dynamics of the liquid and the ions and the chemical species in the electrolyte. So I'm going to skip this one because this is just to show how you can handle non-equilibrium problems with the Green's function and the Kelvin's formalism. You have already seen that along the tutorial, in the school. And there is something that I wanted to mention here, which is that we are doing that atomistically at the atomistic level. So we can only afford to do really small systems which are nanometer scale, and systems in which, by construction, the electrodes are really very close to each other. So you can afford to have systems of about a few thousands of atoms at most, and that limits the distance between the electrodes. In real electrochemical problems, you have a much longer distance. The distance between the electrodes are macroscopic. So there is a concern whether this kind of calculation would really represent what happens in a real electrochemical experiment where the electrodes are very far away. And the answer to that is that, yes, these calculations are meaningful, provided that the electrodes are sufficiently far away so that the structure of the double layer in both sides is really well described. So the double layer screens out the field produced by the external electrodes or the metallic electrodes with a decay length which is characteristic of the electrolyte and the solvent. So if your system is large enough so that this double layer is well reproduced, what you have in the center of your slab will be essentially the behavior of the liquid or the electrolyte in the bulk. Okay, so provided that this distance is large enough so that the double layer in both sides is well described, these problems, this approach will be meaningful, and it will give you physics and science which is relevant for the experimental case in which the electrodes are very far away. And that depends on the electrolyte. So if you have water, for instance, you have a very high permittivity liquid that screens out the field very efficiently. So you will need a relatively small cell to screen out the field. And of course, if you have counterions in solution and you have a high concentration of counterions, this double layer will be very, very narrow, and you will afford to do that. If you have a liquid which is not polar, it has a low permittivity, and also you have a very low concentration of ions, you may need very, very large cells to reproduce this double layer, and things will get much, much worse. Okay, so this is what I'm going to show. This is the kind of system we have been playing with. We are playing with gold electrodes, which are very simple and very easy to describe, and water. And in particular, we have been doing work with pure water, but also with water with some counterions, in particular sodium and chlorine, at relatively large concentrations of 1.25 moles. And we are using a cell which is relatively small. It's only 3 by 4 in the plane of the surface, so it's 12 atoms per layer. And we are using 2 layers in the contact region on each side, and then 4 layers of the electrode in the transistor setup. And then we're using about 40 water molecules between the two electrodes, which is something like 17 angstroms between both electrodes. We are using standard DFT with the van der Waals functional. We are using just the gamma point, which is really a bit too small, but it gives you reasonable results. The grid is 200 Rydbergs, and we are using a quite nice basis set double slit polarization. And we are doing molecular dynamics runs of about 4 picoseconds with a Bertrand thermostat to fix the temperature. In the tutorial, you're going to be doing the same system that I'm going to show in the talk. The only thing is that we are using a much smaller basis set, just single zeta, to make the calculations feasible for you to reproduce in the limited time of the tutorial and in your laptops. So everything will be the same as I'm showing you in the talk, just with a smaller basis set, which is not really enough. And some of the data that I will show you in the talk will not show up with this basis set, single zeta. And we will also use a smaller real space mesh to make the calculation quicker too. Okay, so this is the first result that I want to show you. This is the calculation when you have the same system. So this is some equilibrated water in the middle of two electrodes called electrodes. And we are doing two calculations, one with 0 volts and the other one imposing a voltage of 2 volts between both electrodes. And I'm showing you here the profile of the electrostatic potential in the system as a function of theta, of the position along the sandwich. And you can see here the oscillations in the potential within the gold electrodes and the different potential that happens when you go to the water layer. And that's with 0 voltage. So you see that the potential in the right and left electrode align perfectly because there is a 0 voltage imposed between the two surfaces. The red line here shows the average in the distance of the interlayer planes of gold. So this is a macroscopic average. It's an average of the potential that is really flat inside gold, and it doesn't show these atomic oscillations that you have seen in the black curve. Now, if you do the same calculation with 2 volts of difference imposed between the two electrodes, you see something which is very similar, but you see that there is an offset between the potential in the left and the right electrode, which corresponds precisely to the 2 volts that we are imposed. Okay, but the potential looks very, very similar. If you compute the difference between both potentials, potential of 0 volts and potential of 2 volts, then you can actually start seeing something. You see that there is this drop in the potential of precisely 2 volts between the two electrodes, and you see that the potential drops somehow along the water layer. If you would have a system with no water, then you would see that the drop will be linear. If you have this thing in vacuum, two electrodes in vacuum, you would see a linear drop in the potential along the vacuum, which is just what corresponds to a capacitor with vacuum in between. Here you see the oscillations because the water molecules see the field which is produced by this voltage difference, and these molecules polarize. The charge density of the molecules will polarize to the field, and that's what gives you these oscillations in the potential. This is what you will not see if you have a basis set which is single zeta, which is the one that you will use in the tutorial. With a single zeta basis set, the single zeta is not polarizable. It cannot polarize in the presence of an electric field. You need a double zeta basis and polarization functions to have the molecule polarized. So you won't see these oscillations in your calculations. You will see a linear drop, which is very similar to the one in vacuum. Okay. Now you see that something interesting here already is that this would be the drop in vacuum or with no polarization of the water molecules, but actually the water molecules do polarize, and in the center of the slab, the effective field that you feel in the water layer is much smaller than the one that you would feel in vacuum, and that's because of the charge polarization of the water molecules. So with the water molecules even not moving, just the charge density of the water molecules is polarized, and that screens out very significantly the potential. That was what I was mentioning before, that water is very polarizable. It has dipoles that will orient, but it also has a charge density that can polarize in the presence of the field. So the electric field is much smaller than the one that you would expect just with vacuum. Okay. All right. So now we can do dynamics. We can actually make the atoms move, both in the presence of 0 volts or an external voltage of 2 volts, and you will have different dynamics. Then you have here an electric field which is very, very strong. Actually, we are putting a 2 volt potential in a very, very small distance, so the electric field is really huge. And you can see in the end of the simulation that in the left part, the water molecules are very randomly distributed. There is no clear orientation of the dipoles. Each dipole is oriented in a different manner. But on the right, all the molecules are essentially looking upwards. So all the hydrogen atoms are looking up, and all the oxygen atoms are looking down. And that's because of the field. The oxygen atoms will move towards the positive potential, and the negative atoms will, the hydrogen atoms will move towards the negative potential. Okay. So you see that the water layer polarizes very much in the presence of the field. And you can see that looking at the distribution of atoms, for instance, along theta. If you look at hydrogen, well, you see, first of all, that this liquid is essentially a nanoliquid. It's a confined liquid in a nanospace. So it's not really homogeneous. It has this very pronounced layering. You can see essentially 5 layers of water here, both in hydrogen and in oxygen. You have a much more constant distribution in the center of the slab, but it's clearly a layered liquid. But when you put the potential, you see clearly that hydrogen tends to move up. It moves closer to the negative surface, and it moves away from the positive surface. So you see this double layer, this double peak structure here, and this peak moves to the right compared to the one with no voltage. And the opposite happens with oxygen. Oxygen tends to move towards the positive electrode. Okay, so and the layering is also more pronounced in the case of 2 volts. Okay, you see that there is this peak in oxygen that is more pronounced than in 0 volts. But the main message here is that the water molecules reorient their dipoles to respond to the field, and that's it's very strong. The effect is very visible. You can also see it if you look at the distribution of angles. I'm not going to describe this into detail, but the distribution of angles when there is 0 voltage is essentially random. You can see this broken line is what would be ideally random distribution of angles in the water liquid, and the histogram is the histogram along the MD trajectories. That's for V equals 0 up and for V equals -2 down. And you see that, for instance, this angle theta, which is the angle between the normal to the surface and the dipole moment of the water molecules, is very much shifted towards small angles. So it means that the water molecules will essentially align along the field, along the direction of the surface.
Okay. I think my mic is not working. Can you hear me?
Yeah, we can hear
you. Yes, we are
fine.
hearing.
Okay.
No problems.
My mic ran out of batteries, so
But we can hear you. No worries.
All right. So then let's look at what happens with the charge density in a bit more detail. So I'm going to show you what happens first in the interface between water and iron and gold without an electric field. So this is what you would get in the transiesta calculation with 0 field in the whole system, water plus the gold electrodes. This is the charge density that you obtain. And you can analyze that comparing that charge density with the charge that you would obtain with the 2 fragments separately. So you compute, for instance, what is the charge density of the gold electrodes without water and the water without the gold electrodes. And this is what I'm showing you in the middle panel. So the black full curve is the one of gold, and the broken line is the one with just water. Okay, so you see that apparently they are very, very similar. They seem identical. If you subtract them, you get the change in the charge density due to the interaction and the chemical interaction between water and gold, which is this low figure. Okay, you see that the scale here is much smaller than here. So the change in the charge density of water and gold when they get together is very small, but it's very important. So you see that there is some transfer of charge, some missing charge in the surface of gold, and some extra charge in the first layer of water. So there is a small charge transfer between gold and water in this particular system, and that's just the chemistry of this system. Okay, you can quantify these charges. You can, for instance, compute the Mulliken charges on each of the atoms, and I'm showing you the charges as a function of time during the simulation. This orange one is the charge on the gold electrodes, on both electrodes actually added up, and the red one is the charge on water. And of course, the system is neutral, so the charge in gold and water cancel each other perfectly. They are just mirrors one of each other. And you see that the charge, the Mulliken charge, the transfer of charge is relatively small. It's only 0.2, but there are many atoms here, so it's a really quite small charge. So there is not a strong link, a strong bond between both systems. It's just a very small charge transfer. Something that was not really so much expected is the fact that there is a significant charge transfer between both electrode layers, between both gold electrodes. And this is what I'm showing you here. The one on the left with orange is just the sum of all the charges in all the atoms in both electrodes. But here on the right, I'm showing you the charge on each electrode separately. The one, the brown one is on the top electrode, or the right electrode here, and the yellow one is the one in the other electrode, the left electrode. And you see that the charges here are much larger than the charge, the total charge in gold, and they mirror each other. So when one electrode gets a positive charge, the other electrode is losing an equivalent charge. So the average of these two is what I'm showing you in the left, but both electrodes have a very, very different charge, and actually much larger than the charge in the total electrode. And that was a bit surprising for us. We didn't expect that. But when you think about it, it's easy to understand why this happens. And the reason why this happens is the following. So you have two electrodes, and in the middle you have water, and this water is moving. So you are doing dynamics of the water, and the water is moving with time. And what happens is that instantaneously, this water layer may have a dipole, because instantaneously the dipoles of each water molecule may be adding up in the same direction, and you may have an instantaneous dipole which can be quite large, actually. Okay. And if you look at the charges in the electrodes, this is just the difference between the charge in the top and the bottom electrode, and you correlate that with the dipole of the water layer in between, you see that they perfectly follow each other. When the dipole is large, the charge transfer is also large. When the dipole is small, the charge transfer is also small. And what is happening here is that if you have a structure in which you have a very large dipole in the water layer in between the two electrodes, the electrodes are metallic, of course, and that will generate surface charges in the electrodes to screen out the dipole of the water layer. So if you have a negative, a dipole like this with negative on the left and positive on the right, you will generate charges in the left electrode which are positive and in the right electrode which are negative. That will screen out the dipole of water. And this is what makes this charge transfer between the left and the right electrode. Is a charge transfer which is needed to compensate completely the dipole created by the water layer. And that's why you see this correlation between dipole and the charge between the electrodes. And that's very important. We didn't expect these oscillations of dipoles and oscillations of charges to be so large as they really are. Okay. Okay, so let me go to the other aspect of the calculations, which is what happens when you put a potential. And I'm going to show you the results when you don't have any water. So this is just a capacitor with vacuum in between. You have the system, the solution with an external voltage, and you compare that with the solution with a zero voltage. And when you have, if you compare the density of these two systems, is just that the charges in the metal accumulate on the surface layer of the metal, and you have a negative charge in one surface and a positive charge in the other. And that makes the field to be completely flat inside the electrode and makes the potential drop linearly in the vacuum region. This is the standard behavior of a capacitor, right? What happens if you have water? If you have water, we have the same thing, just with water in between, and you can do the same calculation. You can compute the charge when you impose the voltage and compare it to the charge with zero voltage. And I'm doing this at the same geometry. So the water layer has the same geometry in both calculations, right? I'm just changing the potential. And what you see is something which is very, very similar in the electrodes, in the surface. You see that there is a peak, which is almost exactly the same as the one when there was no water in the left electrode, the same peak in the right electrode. And then you have, of course, some oscillations, again, because water is polarizing. You have a field, and the field polarizes the molecules, and that creates some oscillations in the charge density in the layer. But the screening charges that you have in the metallic surfaces are just the same as you would have in a capacitor with no water. Okay, and this is just Poisson's equation. You need the same charges to screen out the same potential in the same if you have the same geometry. Okay. Now it's important to see that this is just with using a fixed geometry. Okay. Now again, when you have a system like this one, and the atoms are moving, I was showing you before that there is a dipole which is forming. And the point now is that the dipole will be different depending on the external field. Okay, if you have a external field, you have a potential like this, which is very large. The water layer, the water molecules will orient themselves along the field, and they will create a dipole which is different from the dipole that you would have at 0 volts. And actually, this dipole will be very large. So for instance, I'm showing you here the dipole that will happen in the water layer when you impose a voltage of 2 volts. And it's a huge dipole, and it creates a huge electric field inside the water. It creates a very large depolarizing field. And of course, this field will be screened out by the metallic leads. Okay, again, the metallic leads are metallic, and they will screen out all the external potentials. Okay, so I'm showing you here the same system as before, but now I'm comparing different things. I'm comparing on the bottom the situation that you have in the whole system with the potential, but then I'm comparing that with the charge that you would have in gold and in water separately. So here somehow I'm also including the field that you need to polarize the water. Okay, before I was showing you just the field that you need to impose the voltage, which is just the same as the one that you need in the vacuum. But here I'm showing you the field that you need to impose the voltage and to impose and to screen out the polarization of the water molecules. And you see that the charges in the surface are much bigger now than before. Before it was this small peak here, and now it's this huge peak. So you need an extra field, an extra charge to compensate for the dipole that you are creating in the water layer. Okay? And that's just the physics of a capacitor. If you have a capacitor with a dielectric constant or a permittivity which is high, you need more charges on the surface to screen out the potential and to create this voltage difference compared to the one that you would have in vacuum. And actually, that gives you a way to compute the permittivity of your liquid. Oh, sorry. Something is popping up here. Okay. So if you look at the capacitance of a capacitor, you know that depends on the dielectric constant. And by comparing the charges in the capacitor with no water and the capacitance of and the charges of the capacitor with water, you could get an estimate of the dielectric constant of your water layer. We've done that in this case, and we obtain for 2 volts, we obtain a dielectric constant or a permittivity which is about 8. There are 2 things here. One is that 2 volts is probably too large. It's saturating the polarizability of water, and it gives you a dielectric constant which is too small because all the dipoles are essentially aligned along the field, and you can no longer polarize anymore the system. So it's a lower estimate of epsilon. Actually, if you do the calculation with a much smaller field, about 10 times smaller, you get a permittivity which is quite high. It's about 13. Okay. Now the second thing is that this number is very far from the permittivity of bulk water, which is about 80. But actually, we're not computing bulk water. We are computing a water of layer which is nanometer size confined in a nanometer slit. And actually, there are some recent experiments by the group of Undergame in Manchester, where they experimentally find what is the dielectric constant of water as a function of the thickness of the layer in nano-confined water. And for distances of about 17 angstroms, which is what we are using, they found an electric constant about 20, which is not so far from the one we are obtaining of 13. Okay, so we are obtaining numbers which are very, very close to the experimental estimates of the group of Undergame. Okay, another way to compute the permittivity would be not to compute the charges like we did here. These are Mulliken charges that we use, but would be to compute the dipole, for instance. With the dipole, you can also compute the permittivity. And we've done that as a function of the voltage imposed. You see that for small voltages, the dipole scales linearly with the voltage, which is what you would expect in linear response. And that would give you a permittivity, which is about 13, 12, and so on. But then when you have a larger voltage, again, the molecules are saturated, the polarization is saturated, so this dipole moment saturates and bends and is not linear any longer. So you can compute the dielectric constant from that, and we obtain again numbers which are very similar to the ones we were obtaining, and this decrease of the dielectric constant with very large voltages. The error bars here are not really error bars, are the width of your distribution. So you don't have a single dipole here. If you put a voltage, the dipole changes with time during the simulation time, and you have a distribution of dipoles which has this typical width. This is the standard deviation of the distribution of the dipoles that you would have in your calculation. So you have a width of the dielectric constant, which is the one which is shown with the bars. Okay, so just to finish the presentation, getting too long, just wanted to show you some cases in which we actually have an electrolyte, when you have some counterions which are in solution. And we started with chlorine, and I'm just showing you some molecular dynamics, again with 0 volts and with -2 volts. With 0 volts, what happens here is what I was showing you in one of the first slides, that the chlorine atom gets attached chemically to the surface, and that's what is called selective absorption. When you put a negative voltage, chlorine is a negative ion, an ion, and so it gets repelled from the negative surface and gets attracted by a positive one, so it shifts towards the negative one. So you can see that here, the position of the ion as a function of time. In the negative voltage, there is a drift of the ion towards the positive electrode. It's very slow because the diffusivity of the ions is very slow, but in this typical time of a few picoseconds, you can actually see it. This one is the same thing, but just with 2 counterions, with sodium and with chlorine. And again here, if you don't put any voltage, chlorine is essentially not moving, but sodium will quickly attach to one of the surfaces, to the near surface. When you put a voltage of +1, then chlorine gets attracted by the positive electrode, and sodium gets attracted by the negative, so they drift. And you see that there are different drift velocities for both ions, and that's quite consistent with experiments. In experiments, the chlorine atoms in water, or ions in water, have a higher diffusivity than sodium. So we are getting something which is, it correlates well with the experiment. One thing which is interesting is that the fact that you see that in this case in sodium gets attached very quickly to the surface, and there is some chemistry going on there. If you look at the Mulliken charges of the 2 ions, for chlorine, which stays away from the surface, the Mulliken charge is very close to -1, to the nominative anion charge. Sodium, when it's far from the surface, is about a charge of 0.75, which is close to 1. But when it gets in contact with the surface, there is a very large change in the charge, because there is a chemical bond between sodium and the metallic electrode. So the sodium essentially loses the positive charge. Okay. With +1 volts, since both atoms or both ions are very far from the surface, they are never in contact with the surface, the charges are essentially constant. So they are ions which are moving in the solution. Okay, and with this I will finish. Summary is that, well, I think it's clear that non-equilibrium Green's function techniques are really a viable methodology to study electrified metallic and electrolyte interfaces from first principles. It's expensive, but it's feasible. All these calculations that we're showing were done in about from 100 to 200 processors, and essentially they took about 1 minute of real time, of wall time, per molecular dynamics time step. So simulations of a few picoseconds would only take a few 2, 3, 4 days. Okay, so this is really something which is feasible. The external potential is explicitly imposed and as an intensive quantity, which is what you need to correlate with experiments. I've shown you molecular dynamic simulations for water, both pure and containing ions. And one important message is that water is really very well able to screen out the electrode potential very efficiently by polarization. And that polarization comes from both from the molecular polarizability, the distortion of the electronic charge as a response to the electric field, and also from the reorientation of the ions, of the dipoles of the molecules. And this is a very strong effect. And I've shown you that the dipole moments, it shows a very large fluctuation. The dipoles are fluctuating very much by a large amount on a picosecond time scale. And you can use the simulations, for instance, to estimate the permittivity of water, which in our case compares quite favorably with the experiment. And I've shown you that ions in solution show the expected behavior. And they also hint to the viability of addressing chemical reactions. I've shown you that when the ions get in contact with the surface, there is a chemical reaction, there is a change in the charge of the ions, and that can serve as a proof that if you have some chemical reactions of some chemicals in the solution, that will be able to be stimulated by this kind of approaches. This is something that we have not finished yet, but we are working on that to really study chemical reactions and real electrochemistry with this kind of approach. And with this, I finish. Just acknowledge the group. These are the people who have been mainly involved in this work during time. Hernane has become connected to this project more recently, but he has been very useful for us in putting this to work. And again, I thank him very much for helping me to organize this tutorial. Nick, of course, he was very instrumental in having all this running with Transiesta, Alberto Garcia from ICMAP, also to have Transiesta ready to do these calculations, and Mariví Fernández Serra, who was one of the people that originally made the proposal of using Transiesta to study electrochemistry, and which is also a very strong collaborator in this work. I would like to say that our work is hiring now. We are looking for postdocs to do both development of Siesta and applications, and in particular also applications in electrochemistry. And just the last slide, funding, very important. So essentially, especially the Max Center of Excellence, the supercomputing resources in the Spanish network of supercomputing, the ministry, and the patrons of ICN2. And with this, I will finish, and I'll be happy to take any questions you may have.
Thank you very much for the talk, Pablo. So there are two questions here. So you want me to read it, or you want to read by yourself?
If you can read them for me.
Okay. So the first question is from
questions and answers, right?
Yes.
Okay.
We read it.
Yeah, I have it in the screen.
Okay.
Now.
Okay.
Okay, so if we do the Bader charge analysis, the main conclusion is the same. From my personal experience, Mulliken charges are not that trustable. Okay, so that's right. The numbers for Mulliken charges are not very accurate and are not very trustable in the sense of the numerical values. If you use other schemes to compute the charges, you get different numbers. We have not computed Bader charges, but we have computed Voronoi and Huysfield charges. The numbers are different, but the trends are the same. So when you change the potential, or when you do the dynamics, the evolution of the charges is the same as the one that you find in Mulliken. So that's right, the numbers are not solid. Mulliken charges are not physical observables, so it's not something that you can correlate directly with experiment, but they give you a hint of what happens. But in any case, you can compute other kinds of charges, and that will give you the same physical message. Okay, so the question, using all this job, would it be possible to implement it to simulate the transmission function along a single molecule that is electrochemical oxidized reduced in an electrolyte environment? Okay, so this is what I was trying to say in one of the first slides, but probably it was too quick, my comment. My comment is that with Transiesta, the currents that you compute are the electronic currents from one electrode to the other, are ballistic currents electrons flowing through the whole system from one electrode to the other. In the electrochemistry case, that doesn't happen. There are no electrons flowing from one electrode to the other. So if you would compute the Transiesta current, that would give you 0. You have currents because you have chemical reactions in which electrons are transferred from the molecule to the electrode, or vice versa. That's an instantaneous current between the molecule and the electrode. And then you have an observable macroscopic current because there is transport of charge through the molecules or through the ions along the solution, the solvent. It's not electrons that travel the whole way, okay? So to compute the currents, you would have to do molecular dynamics or some other way of computing ionic currents, not electronic currents. Okay. So there is a charge transport by electrons during the chemical reaction, but the actual current that you measure is due to the electrolyte. It's not electronic. So if you would compute the transistor transmission or the current, you would get something which is zero or very, very small. Okay. So this is not physically what the process that you have to compute. Okay, so another question, as we know, is in experiments, the reactions are happening in solvent environment. Here in computation, you have this system, electrode, water, electrode. Could be more realistic if you consider the effect of solvent by some approximations such as the electric constant, etc. Okay, so absolutely yes. You don't need to have quantum water to do this. You could have classical water, and Hernández is the one working on that. He's doing these calculations now with classical water. You could also have a continuous model for water. That would be quite feasible and quite appropriate. You would, in a continuous model, you would probably lose all these effects due to the change in the dipoles, the dynamic change in the dipoles, which may be important. And you would, of course, lose if water is anyhow contributing to the chemistry, to the chemical reactions. Maybe in some cases, water really needs to interact chemically. And in that case, that wouldn't give you the right answer. But in principle, yes, you can remove most of the complexity of the liquid just by using something more classical and not fully quantum. Okay, so do you have for postdoc to develop excitons? No, okay, so excitons, you don't have excitons in siesta. Excitons are an excited state where you need to take into account the interaction between the electron and the hole, and we cannot do it directly in siesta. Maybe in some other approaches like TDDFT that could be done, but not in siesta or in transiesta. As far as I know, maybe Thomas has some more insight on this. Okay, so I'm not an expert in specific absorption, but could you tell me if this absorption is stable? In general, after the potential is removed, the atoms are dissolved, or are they staying there? Okay, so what we found for this particular electrolyte, which is sodium and chlorine, we found this absorption even at 0 volts. Okay, so it seems to be quite stable, at least with in the absence of potential. I'm sure that if you would put the opposite potential, you would drive the ions to be detached from the surface. But so far, we haven't seen that that's driven by the external potential in this particular case. But that's, of course, depending on the molecule and the solvent that you have. That's very much system dependent. There will be many systems in which the absorption is driven by the potential, actually, and it may happen in some potentials and not in some others. Okay, so with this methodology has been applied to chemical reactions. No, that's what I'm saying, that we have not yet done chemical reactions. I think the only kind of chemical reactions in this is this one I showed about the specific absorption of the ions on the electrodes, but that's not really a chemical reaction. That's just more absorption. But we are working on it. I think it will be feasible. You may have the problem of having a chemical reaction in which the barrier is high, so it's an unlikely event. It's a rare event, and you won't be able to observe it through standard molecular dynamics. You will have to have some kind of advanced molecular dynamics, steer molecular dynamics, or doing some kind of infrequent events like Parinello is doing, so on, because the time otherwise should be too large. But I think the physics is right, so you may be able to drive these reactions using these simulations. Okay, so the last question: are you using periodic boundary conditions? I'm using the standard transiesta machinery. So in transiesta, there is everything is done without boundary conditions. So you have the semi-infinite electrodes, you have the Green's functions, the self-energies that connect to your system. You solve a finite part of the system. but you solve it with open boundary conditions. It's not periodic. There is only one part in which we use periodic boundary conditions, which is the solution of the Poisson equation. Okay, there you use periodic boundary conditions just by convenience, but it's not really a periodic model. You're solving the model, which is a finite system, is your contact region and part of the electrodes connected to semi-infinite electrodes. So it's not really a periodic model. Okay. Okay, another question is the model able to predict particle, I don't know what particle means, charge transfer between ions?
Maybe it is partial.
Is it partial?
Partial.
Yeah, so partial is what we find, okay? So if there is a chemical absorption of the molecules or the electrolyte on the electrode, there is always a partial charge. There is never a total charge transfer. So yes, absolutely yes. Actually, if you look at the Mulliken charges, even if the ion is very far from the surface, so you would expect a full charge on the ion, the Mulliken charges that do not give you a full charge because you always have some overlap with the environment molecules, and even if you have a full charge in the ion, that net charge would somehow distribute also along the water molecule. So you never find a full entire integer charge, let's say. But when the molecule is absorbed, there is also always a partial charge. There is a chemical bond, and the electrons are distributed according to the polarization on the molecule and the interface and the surface. So there is always a partial charge. Yes. Okay, so I don't see any other questions.
Now I think that there is one question from one of the panelists.
Yeah, very nice talk, Pablo.
Thanks.
Yeah, I could not ask in the questions and answers. Did you consider the role of temperature and what happens when you change the temperature?
The temperature, you mean the ionic temperature or the electronic temperature? No, we were just doing simulations at 300 Kelvin at the room temperature. We didn't change that. We are using a simple thermostat, but I wouldn't see any problem with that.
Also, I was thinking about this the quantum nuclear motion. I think you mentioned about it when I was writing, so I didn't get it. What is?
No, I didn't mention quantum motion. Of course, quantum motion can be important in water, and we completely miss that in these kinds of simulations. I don't see any essential problem in linking this with quantum path integral things like to obtain the quantum motion of the ions. It would be much more expensive, of course. But yes, water you may have some effects in which quantum effects would be very important. And people are starting to see what happens not only in water, which is now relatively well understood, but also with solvents. When you have solvents in water, what are the effects of quantum motion? Sometimes they are very important, yes. So we are not doing that. We are still very far from that. But in principle, if you would have a large enough machine, I think you would be able to do it, yes.
No, but it could also be that when you look at the difference between zero bias and finite bias, the effects of quantum motion is not so important, or maybe even the effects of temperature. I don't know if you thought about this.
No, I haven't thought about this. No. When you put the voltage, everything is very much constrained, let's say. Water is not so free to move. So for instance, I didn't comment on that. The oscillation or the fluctuations in the dipoles is much smaller when you have a field. It decreases very much because water molecules are forced to be in a given direction. And that may also help in removing the quantum effects.
Right.
You have a very flat surface, of course, quantum effects can be very strong, and the wave function can be very delocalized. If you have a potential that constrains your system, then it's much more classical, let's say.
Right.
So yeah, I didn't think about that. Yeah.
Thanks.
Okay. More.
So some other question?